Yes, welcome back to the continuation of our lectures on electrodynamics, and this is part 4 of chapter 5. Again, our main reference is Introduction to Electrodynamics by David J. Griffiths, and this book is highly recommended for you, so get a hold of a copy of this book. So for today's lecture, we will be dealing with magnetic vector potential. And what is magnetic vector potential? So back in electrostatics, we have the divergence of the electric field is equal to 0, and this permitted us to introduce a scalar potential V in electrostatics such that our electric field is actually equal to just the gradient of the potential, the electric potential. So for magnetic field, the divergence is equal to 0. And so we can write B then as a curl of another vector, because the curl of another vector would be equal to 0. So that is in magnetostatics. So the potential formulation automatically takes care of, by the way, this one is supposedly this one equal to 0. Since the divergence of a curl is always 0, there remains the Ampere's law, which we have discussed in the previous videos. Just like in electrostatics, you can add to V, or the electric potential, any function whose gradient is 0, which say for example a constant, but you're not altering the physical quantity electric field. The same as with in magnetostatics, where you can add a gradient of a function, say lambda here, where the divergence would now look like this. And so the divergence of A is equal to 0, therefore you will be able to have this one. So back in electrostatics, you have Poisson's equation, this one here. So if you replace this one with this one here, then our lambda, in the case of electrostatic, your potential would be like this, but in magnetostatics, our lambda would be this one in magnetostatics. By the way, if the divergence of A sub O does not go to 0 at infinity, we will have to use other means to discover the appropriate lambda, but essentially it is always possible to make the vector potential divergenceless. In other words, the definition of B as the curl of A, or the vector potential, specifies the curl of A, but it does not necessarily say about the divergence. We are at the liberty to pick that as we see fit, and 0 is ordinarily the simplest choice. For this condition in A, Ampere's law becomes this. from the integral form, integral b dot dl equal to mu sub o I enclosed. So that is just the Poisson's equation for the vector potential. By the way, in this case, you're dealing with three Poisson's equation, one in each component, because your A has X, Y, and Z components. And of course, your J would also have to be, we also have to be in three components as well. So you're dealing with this, and this one. In curvilinear coordinates, the unit vectors themselves are functions of position and must be differentiated. So it is not the case, for example, that this one here. So for the other components of the vector potential, you would have to deal with a different form of Poisson's equation. The safest way to calculate the Laplacian of a vector in terms of the curvilinear coordinates is to use this. And remember also, back in chapter 5, using curvilinear coordinates, you must express J in terms of its Cartesian components. So, assuming that the current density J goes to 0 at infinity, then we can read off this solution. So this is a general solution for vector potential using the integral with respect to volume. But if you just have a distribution of currents in a surface or in a line, then you can use this for line currents, and then for surface currents you can use this. By the way, you can take out I out of the integral, but you have to transfer the direction of the current to dl. Now if the currents does not go to infinity, does not go to 0 at infinity, then we have to find other ways to get the vector potential, and some of these are explored in the example which we will discuss later on, and of course in some problems in this chapter of the book. But unfortunately we cannot list down the problems, and if you have a copy of the book, then you can find those problems. So please take a note of this. And of course this one as well. So moreover, since magnetic forces do not do work, A does not admit a simple physical interpretation in terms of potential energy per unit charge, but it can be interpreted as momentum per unit charge. So now let's go to an example 5.11. So in this example, a spherical shell of radius r carrying a uniform surface charge sigma is set spinning at an angular velocity omega. This is a vector quantity. Find the vector potential it produces at point R in figure 5.45. So R could be inside or could be outside the spherical shell. So we could align the angular velocity to the z-axis, but it would be easier for us to solve the problem if we align R with the z-axis, like in this figure here. So suppose that our point lies in the z-axis and that point is r from the center. So this is r from the center, but the point could be inside as well, not just outside, but in general it's anywhere, but we just put the point on the z-axis. So if you look at the figure, here, you can, by the way, our vector potential is, of course, the general formula would be this for surface currents, and then for K you would have sigma V as it was defined earlier. R here, the footed R, is the distance between the source, so any source here to the point R from the center. So that source could also be here, and since we're taking it generally, so we can just consider a point within the surface of the sphere. So in this case, for this particular source point, it's R. This is R from the point, and that R is of course the just equal to this one if you do cosine law. And then of course for sphere you have dA prime equal to r squared sine theta prime d theta prime d phi prime in polar coordinates. So now of course your V, our V here, is just equal to omega cross r prime. So you can review your classical mechanics for that. Here the velocity of a point r in a rotating rigid body is given by this. These are vectors, vector omega cross to vector r prime, and in this case you will have this one, and it is just finally you will have this. And except for this term, this one, everything, every term has sine or cosine phi prime. And since if you will be integrating for the whole sphere, this will just be equal to 0, hence they contribute nothing to the integral, and so there you are only left with this. And so if you do some manipulation by letting u equal to cosine theta prime, then your integral becomes this. By the way, this is positive 1. And now if you have the point r lying outside the sphere, then inside the sphere, then your r is, your big R, capital R, is less than r, and then your expression will reduce to this one. And if it's outside the sphere, then this expression will reduce to this one. The whole expression. So finally your vector potential will have this form, and where your omega cross r is just equal to this. So replacing the omega cross r, we will have finally our vector potential in terms of the natural coordinates. Here is our vector potential for outside the sphere. For inside the sphere, this is this one, and for outside the sphere, it's this one. So as you can see in this result, the field inside the spherical shell is uniform. If you would take the curl of A here. So that's it for example 5.11, and then we'll now go to example 5.12. Find the vector potential of an infinite solenoid of n turns per unit length, radius r, and current I. Now let's move on to the next example. Find the vector potential of an infinite solenoid with n turns per unit length, radius r, and current I. So we cannot use here this equation. Let's go back. Sorry for that. And so we can't use these equations in that problem. But if you notice that the closed integral of A dot dl, this is just equal to this one by the Stokes theorem, and then your curl of A is just equal to B, and this one is just like what? This is just like that's just like Gauss law, where phi is the flux and B is the magnetic field through the loop in question. And also, if you, similarly, it is also the same as the Ampere's law. If you look at this, where the Ampere's law are this one, if you replace A with B and B with A and your mu I enclosed with phi. So if you have symmetry in the problem, then you can determine A from phi in the same way as we got the magnetic field when you have an I enclosed in the Amperian loop. This problem is analogous to the Ampere's law problem of a fat wire carrying a uniform distributed current. So here the vector potential is circumferential. It mimics the magnetic field of the wire using the Amperian loop with radius S inside the solenoid. So we have this one, and of course this is equal to phi, which is this one, and phi is of course given by this, and this is your magnetic field, this one here, and your the area of the Amperian loop. And this one is of course your A, and your dl is the circumference of the Amperian loop. So therefore you get a vector potential of this form inside the solenoid. However, outside the solenoid, the flux is equal to this one, since the field only extends out to R. It cannot go beyond R. So therefore your field, vector potential outside would be given by that. So that's it for example 5.12, and then we move on to the next section. So we summarize magnetostatics, and then we will also discuss the boundary conditions for magnetic fields. And so in similar fashion as in the electrostatics, we have this triangular relations between magnetic field, vector potential, and current distribution, current density. So this is how you calculate magnetic field, and given the current J, current density J, and this is the integral form, and this one given the current J also, this is your vector potential, and these are the differential equivalents to formula. And then you have the relationship between A and B. So the B is just a curl of A, and of course the divergence of A is just equal to 0. So there's one missing link in the diagram, the equation for A in terms of B. So, well, if you have time, you can see problems 5.50 and 5.51. Unfortunately, we cannot list all the problems here, so if you have the book, please take a look at those problems, and if you have time, you can also answer those things. So just as in the electric field suffers discontinuity at a surface charge, so is the magnetic field. It is discontinuous at a surface current, because, well, the presence of current makes it discontinuous. So this time it is the tangential component that changes, unlike in the electric field where the perpendicular component changes. So it's now tangential because it's magnetic field. So if we apply equation 5.48, I should just write it here. Divergence of B is equal to 0. You won't scroll back because it's already far from here. Its integral form is this one. This is the differential form. Now we wafer in a thin pillbox straddling the surface. So the perpendicular components is continuous, as we discussed earlier. Only the tangential component that changes with the magnetic field, unlike in the electric field. So anyway, we can put a wafer thin pillbox as our to cut a portion of the surface. So as for the tangential components, an Amperian loop running perpendicular to the current yields this one. So you have this, it encloses current mu I enclosed, which is just mu's of OKL, as you have seen in the previous calculation. So therefore the tangential discontinuity would be this one here. So if you look at this figure, so K is going there and your Amperian loop is here. So the or this one, you have B above and B below. So you will have of course what contributes to this one is just the length here above. So you will have this discontinuity. So again, the magnetic field, if you have a sheet with current, the magnetic field that's perpendicular to the sheet are continuous, meaning it doesn't change. So if it's B1 below, it would be B1 above. But the tangential components will have a discontinuity. So just remember this. This is just the continuity of the magnetic field. And so if you add, if you consider both components, then this is just your discontinuity of magnetic field. So just like the scalar potential in electrostatics, the vector potential is continuous across any boundary. So the vector potential is continuous at any boundary. So both the perpendicular and the tangential components of the vector potential are continuous. But the derivative of A in here is this discontinuity of B. Of course, you have A being B being a curl of A, so that is natural. But in this case, you have a negative sign, and here you have a positive sign here. But anyway, you can if you do the problems, you will be able to explain it to yourself. So the next section is multipole expansion of the vector potential. So if you want to approximate the vector potential at a localized current distribution valid at distant points, so if you go far away from a surface current or a current distribution, you will have to do multipole expansion, just like what we did in electrostatics, where you have a dipole, and then when you go far away, you have you can see a different field for that. There's actually electric field is not equal to zero, but you will have a kind of field that does not disappear. So remember, the idea of a multipole expansion is to write the potential in the form of a power series in 1/r. So we just have to do this, and then, well, of course, r there is the distance to the point in question. You have a source point and to the point in space. This is the r. So if r is sufficiently large, the series will be dominated by the lowest non-vanishing contribution, and the higher terms can be ignored. So if this is your r, This can be written as this one, or in terms of series, you can also write this in terms of the Legendre polynomial, as we have studied in chapter 3. So accordingly, you can write this one, your vector potential, as this one here. So more explicitly, you have this one, but you have this one, but this one can be I mean, yeah, this one is of course for different geometry. Well, this one is for a monopole term, and the second one is for the dipole, and then this one is for the quadrupole, and so on, if you continue with the series. So what happens is that the magnetic monopole term is always zero, for the integral is just total vector displacement around a closed loop. So the closed integral of dl would be 0. So that is just equal to 0. And so this means that magnetic monopoles do not exist in nature, unlike point charge, where the electric field diverges from the point charge. In this case, by the way, this one is divergence, or the divergence of B, this one. So this is 0. This means that there's no monopole in nature. So in the absence of any monopole, the dominant term is the dipole, this one. So, but there are some rare cases where the dipole also vanishes. So by the way, you can rewrite this integral as this one, where you can write this one here with this one, and then of course you can use the where your c is a vector c in that equation. So maybe I should write that equation. That is just integral of c dot r dl is just equal to a cross c. So in that case, this one here you can rewrite as this one. This one, actually these are equal, and then you write this as this one. So then your dipole vector potential in the dipole term is equal to this. Where your m here is the magnetic dipole moment, and which is just the current times the integral of the area of the surface in consideration. In there, A is the vector area of the loop. If you could look back in problem 1.61, if you have the book, if the loop is flat, A is the ordinary area enclosed with the direction assigned by the usual right hand rule, fingers in the direction of the current. So example 5.13, find the magnetic dipole moment of a bookend-shaped loop shown in figure 5.52 here. You can actually so this one is the loop, and you can actually divide this one, this loop into two loops, this one here and this one here, the one perpendicular and the one parallel to the XY plane. And look at this, there's no current actually here, there's no current here, but actually if you divide them, you have current going this way and a current going this way, so it just cancels if you join them together, but separately of course they have. So going back, so you could consider the wire to be a superposition of two plane square loops in figure 5.53. The extra sides AB cancel when the two are put together, since the currents flow in the opposite directions there. So the magnetic dipole moment, going back to the formula, M of M, which is just this one, so I times the cross-sectional area. So the net magnetic dipole moment would be for this part here would be this one, and for this part would be this one. So for here you will have an M going this way, and for this you have an M going that way. So it is clear from equation 5.84 for the magnetic dipole moment that it is independent of the choice of origin. So you may remember that the electric dipole moment is independent of the origin only when the total charge vanishes. If you go back to multiple expansion of dipoles. So it is independent of the origin, as magnetic monopole moment is always zero. So although the dipole term dominates the multiple expansion unless M is equal to 0, and thus offers a good approximation to the true potential, it is not ordinarily the exact potential. There will be quadrupole, octupole, and higher contributions to the potential very far away. So may I just read the three bullets? You might ask, is it possible to devise a current distribution whose potential is pure dipole, for which equation 5.83 is exact? This one here, and then this one. The answer is, well, yes and no. Like the electrical analog, it can be done, but the model is a bit contrived. To begin with, you must take an infinitesimally small loop at the origin, but then in order to keep the dipole moment finite, you have to crank up the current up to infinity with the product M equals IA held fixed. So in practice, the dipole potential is a suitable approximation only whenever distance r greatly exceeds the size of the loop. So when you're really far away, So you can only use the dipole potential approximation if the point is really really far away from the source point. And the magnetic field of a pure dipole is easiest to calculate if we put m, vector m, at the origin and here, and let it point in the z direction. So our magnetic moment points in the z direction, and point r is here. So what happens is that from m cross r, we will have m sine theta phi. I mean, so this is r hat, sorry. So this is m sine theta because this is sine theta. I mean theta, the angle is theta. So you will have this one as your dipole, I mean vector potential, very far away for a pure dipole, dipole. So if you get the magnetic field, you just get the curl of A, and then the curl of A will just be the magnetic field of a dipole far away, and this is just equal to this one. So talking about magnetic fields, you have here a magnetic field, and this one is just two charges, positive and negative. So surprisingly, this is identical in structure. As you can see, almost the same to the field of an electric dipole. If you go back to the discussion in chapter 3. So up close, however, the field of a physical magnetic dipole, a small current loop, looks quite different from the field of a physical electric dipole, plus and minus charges, which is separated by short distance. So if you I'm sorry class, but these are for magnetic dipole, and this one is just for a pure dipole, and this one is for a physical dipole. So if you look at the electric dipole, I mean for two charges, it looks different, really different from well, they are similar for the pure dipole, but for a physical dipole between 2-point charge, positive and negative, it looks like this. And so it extends like a pumpkin, not like this one. So it's so different here. So I think that's it for our lecture in chapter 5. We will move on to the next chapter next week, and I hope you've learned something from this lecture.